Greetings everyone, and welcome back to the next video in our online lecture series for CHE 2300. In today's video I am going to cover how to calculate convective heat transfer coefficients when we have heat transfer that's associated with a phase change, that is, heat transfer that's associated with some type of condensation. So the scenario I want you to envision is that we have some hot vapor, and that vapor is condensing on, in this case, a vertical cool surface. At steady state, I will form some condensate film. That condensate film will have a film thickness of delta. That film thickness will be a function of Z, or how far down the wall I have traveled. Eventually I will travel far enough down the wall where I will reach steady flow and the film thickness will not vary anymore with my position. In this particular image, I have my cool surface. It is being held at a temperature T sub naught. And the temperature at my vapor-liquid interface is the dew temperature of my vapor. Because that vapor is condensing, accumulating, it begins to flow down that vertical surface. So if we can dig deep into our memories here, I'm going to write the velocity profile. So the Z component of the velocity as a function of Y for my film condensate, or my condensate film, I should say. That is equal to rho G, the thickness of my film squared, divided by 2 mu. All of that multiplied by 1 minus Y divided by the thickness squared. Hopefully that equation looks somewhat familiar to everyone. Again, that is the velocity profile that is describing how the velocity changes as a function of position moving away from or towards the wall. The flow rate per unit width of film is is given by the condensate liquid loading. I want to point out this is for vertical surfaces. Well, I guess specifically this would be for a vertical tube. The liquid loading is defined as the mass flow rate of condensate. So I forgot to highlight that here. My vapor condenses on my cool surface. It forms a film. That film begins to flow down that surface. It is flowing down that surface at some mass flow rate that we are going to define as omega. So our liquid loading on that vertical tube is equal to omega divided by pi times the diameter of that tube. We can use that condensate liquid loading to define a Reynolds number for our condensate film. So again, this is for vertical surfaces. The Reynolds number is defined as the condensate liquid loading divided by the viscosity of the condensate film evaluated at the film temperature. And I will highlight what I mean by film temperature in a couple of pages. So, much like all of the other heat transfer problems that we have been introduced to, typically our goal is to calculate some convective heat transfer coefficient, maybe an individual convective heat transfer coefficient, or maybe using that individual heat transfer coefficient to calculate an overall heat transfer coefficient. In any case, the first thing we need to do is calculate the Reynolds number of our fluid that is moving. Because again, the equation that I use to calculate that convective heat transfer coefficient depends on the flow regime of the fluid, in this case, the flow rate of that condensate film. So for for convective heat transfer with condensation on a vertical tube or wall, the convective heat transfer coefficient for laminar flow, and I'll talk about that number here in a second, I can use the following equation, which tells me the convective heat transfer coefficient is equal to 2 times the square root of 2 divided by 3. That is multiplied by the thermal conductivity of my film, evaluated at the film temperature, cubed, the density evaluated at the film temperature squared, local acceleration or local gravity constant, and the latent heat of vaporization divided by the viscosity evaluated at the film temperature multiplied by the length of that tube or wall, and that is multiplied by this temperature difference between the dew temperature, or the temperature at the vapor-liquid interface, and the wall temperature, which we are representing as T naught here. That entire quantity is raised to the 1/4 power. And so here again, I'm going to point out that this would be for Reynolds numbers that are less than 350. Here, for condensate for condensate film flow, when we calculate Reynolds numbers, we are going to define our flow regimes, the cutoffs for our flow regimes differently than we would for, say, flow in a circular pipe. So for this particular scenario, a Reynolds number below 350 is defined as laminar flow. If we calculate our Reynolds number and it is above 350, we are in the turbulent regime, and the following empirical equation can be used. So my convective heat transfer coefficient is equal to 0.003. That is multiplied by the thermal conductivity cubed, the density squared, gravity, this temperature difference between the dew temperature and the wall temperature, the length of my vertical surface, viscosity cubed, and the latent heat of vaporization. That entire quantity is raised to the 1/2 power. And again, that is for film or condensate film where the flow regime of that film condensate is in the turbulent regime. That is Reynolds numbers that are greater than 350. Here I'm just writing in words what I said out loud. TD is the dew point or dew temperature of the vapor, and delta H vape is my latent heat of vaporization. At the surface, I can define the heat flow for this heat transfer process. So my heat flow is defined as my convective heat transfer coefficient multiplied by the area of heat transfer. And that is multiplied by that temperature difference between the dew point or dew temperature and the surface or wall temperature. That is equal to the mass flow rate of my condensate multiplied by my latent heat of vaporization. Okay, so again, that describes the heat flow that is occurring during this heat transfer process that involves a phase change. I'm not going to talk too much about the following figure other than to point out this somewhat discontinuity in the data where we see a jump or change in the data somewhere in this regime between 250 and 350, and that relates to these cutoffs that we saw on the previous page. All of the equations and nomenclature for this particular chapter I'm taking from a different textbook, so that's why you'll see that here the wall temperature is T naught instead of TW, but that's all being pulled from this particular textbook here, Bird, Stewart, and Lightfoot. Okay, so that covers film condensation on a vertical pipe or vertical wall. We mentioned this idea of calculating the properties of our condensate film at the film temperature. So here the film temperature is defined as the arithmetic average of the dew point or dew temperature and the wall temperature. So much like we had the mean bulk temperature for forced convection, here we have a film temperature, and this is the temperature at which we need to evaluate our properties such as thermal conductivity, density, and viscosity. We can also write the equation for film condensation on vertical tubes for laminar flow. Right, so this is only for laminar flow in the following form. So the convective heat transfer coefficient here is equal to 4/3. That's multiplied by my thermal conductivity cubed, density squared, gravity. That is divided by 3 times my viscosity times my liquid loading. Those are on top of each other. Let me separate those, gravity and liquid loading. That entire quantity is raised to the 1/3 power. So I have two equations that I can use for condensation on a vertical tube if I'm in the laminar regime. And it just may depend on what information I'm given for that particular problem. For film condensation on horizontal tubes, for laminar flow, we can use the following equation to calculate the convective heat transfer coefficient. That is equal to 0.954 multiplied by thermal conductivity at the film temperature cubed, density at the film temperature squared, multiplied by gravity. We multiply that by the length of that horizontal tube. All of that is divided by the viscosity times the mass flow rate of our condensate, and that entire quantity is raised to the 1/3 power. If we have moderate temperature differences between the dew point and the surface temperature of our wall, we can rewrite equation 9 with the help of an energy balance in the following form. So the convective heat transfer coefficient, again, this is for film condensation on a horizontal tube. The convective heat transfer coefficient can be written as 0.725 multiplied by the thermal conductivity cubed, density squared, gravity, latent heat of vaporization. That is divided by the viscosity times the diameter of the pipe. And that is multiplied by the temperature difference between the dew point or dew temperature and the surface or wall temperature. And that entire quantity is raised to the 1/4 power. Okay. So now we have seen equations that allow us to calculate the convective heat transfer coefficient if I have heat transfer with condensation on a vertical tube, and if I have heat transfer with condensation on a horizontal tube. Now, out in the real world, and we'll talk about this more in our next lecture about heat exchanger equipment, we don't have a single tube. We don't typically have a single horizontal tube. We oftentimes have many horizontal tubes that are stacked on top of each other. That is the basic description of a shell and tube heat exchanger. And so here I'm going to give you an equation that will allow you to calculate the convective heat transfer coefficient for a stack of horizontal tubes. So the average convective heat transfer coefficient for a stack of tubes, H sub n, is given by the following equation. So H sub n is equal to H1, which is the coefficient for the top tube in the stack, capital N to the negative 1/4 power, where capital N indicates the number of tubes in a particular stack. For a stack of tubes, equation 10 becomes the following equation. So H sub n is equal to 0.725 multiplied by the thermal conductivity at the film temperature cubed, the density at the film temperature squared, gravity times the latent heat of vaporization. That is divided by viscosity times the diameter multiplied by the temperature difference between the dew point and the surface temperature. And now I have this additional term in here that accounts for the number of tubes in a particular stack. And that entire quantity is raised to the 1/4 power. Okay, so that concludes our lecture video today on calculating convective heat transfer coefficients for heat transfer with where we have associated, or heat transfer, that is associated with condensation. Please be on the lookout for videos where I go through at least one example problem where we use these equations to calculate a convective heat transfer coefficient.